Welcome back. My name is Renee Clary, and in this video segment we will cover deformation, mountain building, and very briefly the evolution of continents. Deformation is the result of tectonic forces and therefore clearly related to plate tectonics, one of our main themes of the course this semester. In addition, deformation has resulted in many changes on the Earth's surface and is related to the changes in the Earth along our theme of geologic time and uniformitarianism. Let's get started. First, we're going to start with a definition. Deformation simply means how a rock body responds to tectonic changes. Why is this important for us to understand? Well, deformation holds a record of past events for us, so we have a better understanding of how the Earth reacted in former conditions. It helps us to find and recover resources. Many structures that are related to tectonic stresses will hold, for example, petroleum resources. We can also plan structures, buildings, and dams and bridges based on what we know about deformation and how things react to stress. Stress is simply the application of force or pressure. We're looking at force per unit area, and there are three different types of stress. We have compressional stress, we have tensional stress, and finally we have shear stress. Let me show you some diagrams that illustrate this a little bit better. Compressional stress would result if you have forces converging on each other. Clap your hands together and push as hard as you can, one hand against the other. This is compressional stress. Note what happens in this diagram when compressional stress is added to a rock body. We can get bending or folding, and we can also get breaking or faulting. It will depend on the rock. It will depend on how the stress is applied and where it is applied. Tensional stress, we have two opposing forces working in opposite directions. So take your fingers and clasp the fingers of your other hand and pull your hands apart as hard as you can. This would be tensional stress. We find this in divergent plate boundaries. And note what happens to a rock body when tensional stress is applied. We don't see folding, but we do see faulting. And we'll talk about the different types of faults that result from the different types of stress a little bit later in this video lecture. And finally, we have shear stress. This is when force is applied in a parallel but opposite directions. So clasp your hands together and make your right hand move to the top of your left hand, but your left hand wants to move toward the bottom of your right hand, again, while still pushing very hardly against each other. That would be shear stress. And note again what happens with shear stress in a rock body. We're not going to get bending, but we will get breakage or faulting. Strain is the deformation that is caused by stress. And as you saw in the earlier diagrams, it can be different types of deformation. If rocks return to the original shape once the stress is removed, we call that elastic deformation. If the rocks bend or fold, we have plastic deformation. Plastic meaning bending, plastic flow. Again, we're not talking about plastic such as the milk cartons are made of now. And if rocks fault or break, we have brittle deformation. If the temperature and pressure are high enough, we tend to get plastic or ductile deformation because we get bending. If we are closer to the Earth's surface, however, where the temperature and pressure are lower, the deformation usually is brittle. We get breaking or faulting. This diagram shows deformation. Rocks don't tend to behave elastically. We do use the term, especially with the elastic rebound theory, for earthquakes, but in general, rocks don't behave elastically. There comes a certain point where they will either bend or they will fracture. If the crust, however, is loaded with ice, and then the ice subsequently melts, we would have elastic rebound or isostatic rebound. So in this case, the crust would behave elastically. Usually rocks, again, will fold if the pressure and temperature are high enough and the stress is applied slowly. Quick applications of stress or force at cool temperatures and low pressures most often result in rock fracture. Of course, there's a disclaimer with that because that's indicating that the Earth always behaves the same way all the time, and we know that the Earth is very complicated and there are always exceptions. Here we see a fold. Follow that rock along. Okay? So that would be plastic deformation. Here we have a person for scale standing next to rocks that have been broken. Well, how do I know that other than seeing a line right through the middle? We have one rock body that was continuous. Remember, the principle of lateral continuity says that the sediments are deposited equally in all directions until it slowly pinches out, the layer pinches out. So in this case, we have an obvious rock layer that was connected, look on the other side of that breakage, but some application of stress caused the rocks to behave brittly, and we have breakage, fracture, or faulting. Again, remember that sediments accumulate in nearly horizontal layers. We do have cross-bedding, but this is an exception rather than a rule, and cross-bedding does not imply huge folding. So if you see something that is folded or faulted, you know that some tectonic force has been at work and affected that rock body. Now, to describe orientation of rocks out in the field, geologists use two different terms. Strike is the direction of a rock layer that intersects the horizontal plane. So it basically tells us a direction of the rock body if we intersect that rock body with a nice flat plane. Dip, on the other hand, will show us the angle of deviation from that nice flat plane. So the dip is always measured perpendicular to the strike. One of the best diagrams to illustrate strike and dip is one that involves water, because the water forms that nice horizontal plane. Look at these rock layers. They are tilted. That tells us right away something's happened to them, because we know that rocks, sediments are deposited in nice horizontal layers. Now, the strike is the direction when we measure it intersecting that nice horizontal plane. So in this case, we're looking at something that deviates a little to the northwest, let's say north-northwest, and we would give that in degrees. The dip would be the angle formed with that plane from the rock layer to that horizontal plane. So again, strike and dip are perpendicular to each other. In this case, we're looking at a 50-degree angle, so the dip is 50 degrees. Note the little map symbol up in the upper right corner. It shows a T. The T has a much longer top than it does supporting axis. The top part of that T is the strike, shows you the direction, and the little bitty supporting part of the T, the little bitty vertical part, points in the direction of the dip. In this case, there's a 50 below that because the dip is 50 degrees. These symbols are used on geologic maps. Here's a very basic example. Note that there is a kind of peachy rock layer that is exposed, and we see the strike and dip symbol down at the bottom with a 40. So we know that the dip of those rocks is 40 degrees, and it looks sort of a northeast direction for dip, and the strike there is a north-northwest direction. So again, the dip and the strike are measured perpendicularly from each other. That little symbol that has the cross inside means that the rock layers are nice and flat. We have, again, two basic deformation types if we exclude elastic deformation, because rocks typically do not elastically deform. We have folds and we have faults. Let's look at folds first. There are three types of folds. Again, these occur when we have high enough temperatures and pressures, and force is usually applied slowly, and we result in bending or plastic deformation of rock bodies. A monocline is a simple bend or fold. An anticline, the limbs dip away from the axis and the oldest rocks are in the core. And a syncline, the limbs dip toward the axis and the youngest rocks are in the core. Now, what type of stress do you think is responsible for folds? Remember, we talked about tension, compression, and shear. What type of stress do you think is responsible? If you said compression, you're correct. Let's take a look at each of the types of folds. A picture is worth 1,000 words and beyond in this case. Here's a monocline. We have a simple bend in the rocks. Note that we have the strike and dip symbol for the bend, the fold dipping down 35 degrees. Here is one in nature. Let me draw it out for you. That is a monocline. This is in the Bighorn Mountains in Wyoming. A simple bend or fold. Now, anticlines and synclines occur together, and note the axis of each fold. There's a plane moving down the center of each fold. There is an axial plane for the syncline over on the left-hand side, and toward the right there is an axial plane for the anticline. Note that the limb of the syncline, the right limb of the syncline, is also the left limb of the anticline. So again, these occur together. Now, the way I determine a syncline, and I know this is sort of an easy way and a general way to do it, but I've always thought of a recliner, a syncliner as a recliner, and when I first encountered these terms, that's what helped me remember them. You can recline in a syncline. Okay, here are folded rocks in the Calico Mountains, southeast California, and note that we have an anticline here outlined in blue, and we have a syncline here outlined in green, and the anticline and syncline share a limb. Now, how do I know that's a syncline? You can recline in it. Okay, now note that anticlines aren't necessarily hills in their topographic expression, and synclines aren't necessarily valleys. Instead, the folds are referring to the rock layers within the rock body and not how they're eroded in nature. For example, this is a scene in Kootenai National Park in British Columbia, and the syncline is up there at the top of the mountain. It's part of the summit of the mountain. There's a syncline. Now, isn't it great when they're nicely exposed like that in cross-section, but more often than not we encounter eroded folds on the surface. So the way we tell them apart, with an anticline, the oldest beds are in the center. Note that we have a layer and then equidistance from, in this case, equidistance from the middle layer. We have those nice kind of bluish layers, and then we move further away, we get those brownish layers. With an anticline, the oldest beds are always going to be in the center. And there we have two anticlines. The oldest beds are in the center. How would we know they're the oldest beds? We would know that by relative dating, fossils, use of fossils, or we could correlate these to other areas where the rock bodies were actually nice and horizontal, or we could also use radiometric dating to find out which was the oldest. Now, the opposite of the anticline, of course, is the syncline, and the syncline would have its youngest beds at the center. Okay? Now, again, folds aren't naturally nicely exposed in cross-section on the Earth's surface, and they don't always occur nice and symmetrically. Instead, we can have inclined folds which have asymmetrical limbs. We can have overturned folds, and this is occurring when the limbs dip in the same direction because one limb has been rotated more than 90 degrees. We can have a recumbent fold where the axial planes are actually horizontal. A plunging fold means that the axis is not or the axial plane is not nicely perpendicular to the horizontal surface, but instead the fold will sort of move into the earth. Again, a picture's worth 1,000 words in this case. Domes and basins are the oval and circular equivalents of anticlines and synclines. A dome would be the equivalent of an anticline, and a basin would be the 3D equivalent of a syncline. So with a dome, the oldest rocks are in the center, and with a basin, the youngest rocks are in a center. Let's take a look at these. Here we have an asymmetrical. You can see that the limb on the left side is much less steeply inclined than the steeper right-hand side. So this is asymmetrical. Now what happens when the limbs dip in the same direction? One limb has been rotated more than 90 degrees. We have an overturned fold. Note what's going on here too with the strike and dip symbols. For the overturned limb, look at 75. See how the nice little support, the nice little leg of the T has a little loop to indicate that it's overturned and dips at 75 degrees, as opposed to the limb that's not overturned. We have a 25-degree dip. There's the overturned symbol. And finally, if we have a nice horizontal axial plane, this is known as a recumbent fold. This one is called a recumbent fold in Switzerland, but I think I would argue with that a bit. I don't see an axial plane at 90 degrees when I draw this out, but I do see something pretty darn close. I would call this an overturned fold. There are geologists who will argue with me on that. Okay, flunging folds. Again, this is the folds actually moving into the earth, and you can see the eroded expression of that is kind of neat. We get these little loops on the surface of the earth. The bottom photograph is Sheep Mountain Anticline in Wyoming, well noted to many geology field students who have climbed it and mapped it on numerous occasions. And there again is the surface expression. With an anticline, again, the oldest rocks are in the center. With a syncline, the youngest rocks are in the center. Now, how would you know this is an anticline? I mean, you see a topographic expression, kind of a hill, but on a map, how would you know that this would be an anticline? Take a look at those strike and dip symbols and note that the dip is actually moving away from the central axis of that fold. In that case, we have an anticline. In a syncline, the dip moves toward the central axis of the fold. This would be an eroded dome. How do I know? The oldest rocks are in the center. And note again, the dip is moving away from the center. A dome is the equivalent, 3D equivalent of an anticline. And here is an eroded basin. Check out the strike and dip symbols and note that the dip is pointing in towards the center, even though we have a nice flat surface expression. We also know it's a basin because the youngest exposed rocks are in the center. And again, the basin's the 3D equivalent of a syncline. Okay, so we've covered folds. Let's look a little bit about breakage or brittle deformation. A joint is a fracture along which no movement has occurred, and a joint does not necessarily imply that there has been stress. We can get joints through erosion. It does not have to be a tectonic stress, and we do not have to have movement along that fracture. So a joint is a fracture along which no movement has occurred, whereas a fault is a fracture along which movement has occurred. So we're more concerned with the faults. We're looking at brittle deformation resulting in breakage of rock and faulting. Movement has occurred on either side of the fault. Here are some joints in Tasmanian rocks. Because there is a fracture, we tend to have erosion more readily because of the exposed surface area along the fracture. It looks like building blocks, doesn't it? But it's natural. And in this photograph, we do have a fault. Well, how do I know it's a fault? Okay, check out that layer of rock that is now separated from another layer of rock. Same rock layer, but it is now separated along a fault because movement has occurred. If we trace that same rock body along to the right, it looks like we also have a joint there. It looks like a break in the rock, but no movement has occurred. So the difference between a fault and a joint is that with a fault, movement has to occur across the fault. There are different types of faults, and to describe them, we go back to old miners' terms, and we use hanging wall and footwall. Now, a hanging wall simply means, to an old miner, the wall on which he or she would hang a lantern overhead, and the footwall would be the wall along which the miner could walk. Now, we use relative movement. We'll say that the hanging wall moved up and the footwall moved down because we don't know. Unless you're there to actually observe the faulting process to see if one wall moved up and one wall moved down, we're talking about relative movement. So in geology, when you encounter an old fault, we're looking at relative movement. One wall may have moved and the other one may have stayed stationary. They both may have moved. We just don't know. So we're going to talk about relative movement with these faults. This illustrates the hanging wall and the footwall. Note the miner inside that tunnel would hang a lantern on the hanging wall, and the red zone here, the ore vein, note that the other wall upon which the feet are resting is the footwall. Okay, hanging wall and footwall. Again, the miners crawling up in this tunnel, their knees and feet would touch the footwall. They could hang a lantern overhead on the hanging wall. So look in the middle diagram though. How would we know hanging wall versus footwall? The easiest way is to see whether or not you could walk along one surface. For example, if you tried that, it wouldn't work, right? You'd fall off. So that works. Where your feet would touch, that is the footwall. So the footwall here is lower left and the hanging wall is upper right. Vertical faults do not have a hanging wall and a footwall. First, let's talk about dip-slip faults. These are faults in which vertical movement has occurred. We have normal faults and we have reverse faults. Let's look at the normal fault first. In a normal fault, the hanging wall moves down and the footwall moves up. Again, this is relative movement. One may have moved, both may have moved. We just don't know. Normal faults are produced by tensional stress, typically found in divergent plate boundaries or, again, in areas where there is divergence. Here we have the footwall and hanging wall labeled. Note the footwall is moving up and the hanging wall is moving down relative to each other. We can also have something known as a listric fault. In a listric fault, this is a normal fault, but the fault becomes flatter with depth. Very typical in the sediments of the Gulf of Mexico. We get listric faulting and rollover anticlines. Okay, now how would we figure this out? What do we know whether or not we have footwall, hanging wall, movement? Let's figure it out. The first thing is locate the fault. Now, where would the footwall be? The footwall would be designated by the wall along which you could walk. So there's my little stick figure and I can walk up. The footwall in this case would be the portion on the left of that blue fault. Now you check out the rock layers which have been separated. Remember, my footwall is on the left, so my footwall has moved up relative to my hanging wall. The footwall's moved up, the hanging wall's moved down, therefore this is a normal fault. We can also have reverse faults. In a reverse fault, the hanging wall moves up and the footwall moves down. These are produced by compressional stress, very typical along convergent margins, convergence tectonic forces. We are also seeing some thrust faults. These are reverse faults, but they have a very slight dip. They have a dip less than 45 degrees. And thrust faulting is very common along convergent plate margins. Here is a reverse fault. The footwall and hanging wall are labeled for you. The footwall is the one on the right, the hanging wall is on the left. We see the footwall moving down and the hanging wall moving up. Therefore, this is a reverse fault. If we have a low angle, less than 45 degrees, we have a thrust fault. It is a reverse fault, but it's a low angle reverse fault, known as a thrust fault. Here is a fault. The arrows show you the direction of movement. Which one is the footwall? Along which wall can you walk? Aha, so my footwall is going to be on my right. So therefore, my footwall is moving down, my hanging wall is moving up. This is a reverse fault. We can have horizontal movement as opposed to vertical movement. And in this case, we have strike-slip faults. Left lateral or right lateral depending on the direction of movement. And these are produced with shear stress. Transform plate boundaries. Okay, what type of fault is this? You see that the fault is marked right across a roadway. The road has moved, shifted, but check out that cross section. The rocks haven't moved up and down, so this is a strike-slip fault. As you're driving down the road, where is the displaced road on the other side of the fault? It's to your right. So therefore, this is a right lateral strike-slip fault. The road across the fault has been displaced to the right. What about this one? We see in this case we have a road that's been displaced. It doesn't have to be a road, of course. It can be a fence, a rock body, a stream. If we imagine ourselves driving on one side of the road, pick one, doesn't matter which side, and we look across the fault to see where the road has been displaced, you should note it's off to your left. So this is a left lateral strike-slip fault. Naturally, faulting can get complicated. We have oblique slip faults that involve both vertical and horizontal movement. For example, here we go. Note in the cross section that there has been some vertical movement, but also note the displacement of that stream. Okay, if you had to describe the displacement of the stream as either right lateral or left lateral, which would you choose? Stand on one side of the stream, look across the fault scarp, and you note that the river or stream is displaced to your left. This is left lateral movement. But there is also some vertical movement as well. Okay, now that we've described different types of deformation, let's look at mountain building. Mountain ranges are simply a linear association of peaks, and a mountain system would be a combination of ranges. Naturally, mountains can form in a variety of ways. We can have volcanic mountains. We can also have differential weathering and erosion, block faulting, or orogeny. Orogeny is an episode of mountain building on a grand scale. We're going to investigate each of these. Let's start with the volcanoes. Here's the Chalden volcano erupting. Volcanoes form mountains, especially in convergent plate boundaries, also divergent as well. We get volcanic activity in both. Continental convergent plate boundaries do not have volcanic activity. We can also form mountains through differential weathering and erosion. And let's look at plutonic mountains being formed this way. Plutonic igneous rocks imply that these were the magma cooled below the surface of the earth. So we had emplacement of magma which cooled below the surface. However, if the overriding sediments are eroded away to expose those plutons, we can have mountains. We have erosion of batholiths over time. This diagram illustrates it well. Notice in the top we have a lot of overlying sediments. We have an igneous intrusion. It's cooled. We have plutons, batholiths. And if those sediments, those overlying sediments, are stripped away through weathering and erosion, we now see those plutons on the surface of the earth. So we can have plutonic mountains. One of the most famous cases of this is in Yosemite. Block faulted mountains are produced from tensional stress in divergent plate boundaries. Tensional stress produces normal faults, and you may want to review that a bit. Remember, tensional stress produces normal faults. Compressional stress results in reverse faulting. The uplifted areas through this tensional stress are called horsts. Horsts, horsts, and the downdrop blocks are referred to as grabens. Here we have tensional force. Remember, we're moving off, basically pulling the crust off in opposite directions. This is divergence. The uplifted blocks are called horsts. The downdrop blocks are called grabens. The Humboldt Range in Nevada is actually a horst. It's bounded by normal faults. Now, in addition to volcanic and plutonic and block faulted mountains, we have episodes of mountain building, which are called orogenies. Most typically, we're looking at convergent plate boundaries. We have deformed sediments. We also get plutons in volcanoes at these convergent plate boundaries. Most of the Earth's geologically recent orogenies are formed in the Circum-Pacific Belt and the Alpine Himalayan Belt. Each belt has smaller segments known as orogens, and most of the Earth's orogenies, present and past, occur at convergent plate boundaries. Here is an oceanic convergent plate boundary. The subduction complex, that accretionary wedge, is formed from sediments accumulating from being scraped off that subducting plate in the subduction process, and also sediments from weathering of the island will end up in the subduction complex. There we go, subduction complex. As subduction continues, we can have back arc spreading, where the rising magma from the subduction process initiates spreading or divergence in that back arc basin. As subduction continues, the back arc basin closes, and this is going to result in deformation of the back arc basin and the deposits from the continent. So we tend to see metamorphic rocks in orogenesis. Continued subduction results in thrusting of those back arc sediments onto the continent and suturing of that island arc to the continent. And the process of suturing a smaller piece of continental crust to a larger continental body is known as accretion. Similar things occur in oceanic continental plate margins. This diagram depicts an Andes type subduction margin where we have an oceanic plate subducting underneath a continental plate. It started out at the top as a passive margin and then yielded to an active margin. As the subducting plate descended in that middle diagram, dewatering of the plate resulted in magma production. Partial melting creates that magma. The magma will rise because it is less dense. It will rise on the overriding continental plate. If it breaks through the surface, we have volcanoes. If the magma cools at depth, we have batholiths, plutons. Continental convergent plate margins. The famous case, of course, is India colliding with the Eurasian plates. Any oceanic crust between the two would have been subducted with volcanic activity, naturally accompanied by earthquakes. Also, plutons in place as well. However, when there is no more oceanic crust to be subducted, we have crustal thickening, producing some of the highest mountains in the world. This diagram shows collision of the Indian and Eurasian plate, and the Himalayas were uplifted. There's a reference point there, and note the movement of the reference point. Don't forget, however, that in addition to this uplift, we also have roots of mountains. Isostasy tells us that the very tall mountains are also supported by roots, mountainous roots. The Himalayan mountains in Tibet are the highest mountains in the world today. A long time ago, the Appalachian Mountains would have rivaled the Himalayan mountains in height. Because of weathering and erosion, though, the Appalachians were slowly weathered and eroded away. Okay, we're briefly going to discuss continents and the formation of continents. We've already mentioned accreting that volcanic arc to the continent when we looked at oceanic convergence. Continents grow by accretionary wedges, and these are the sediments that are scraped off the subducting plate. Continents can grow by volcanism and plutonism at the subduction zone. That magma rises, creates volcanoes, or if it cools below the surface, we have plutons. And continents can grow by terrains that are added to the continent, fragments of seamounts, island arcs, microcontinents that are accreted and sutured onto the continent. This diagram shows all the different terrains on the western edge of the North American continent, and this is a very generalized diagram. If you move down to a much more detailed diagram of the terrains, it gets really messy, and a lot of geologists specialize in trying to sort that out. So continents evolve through accretion and collision. Island arcs are formed. A collision between island arcs will form a continental core. And in Earth's history, geologists hypothesize that this had been going on at least 3.96, almost 4 billion years ago. The craton is the stable interior part of a continent. This is the core or the nucleus of our continents today. And cratons consist of two different parts. A shield is that part of the craton that is exposed at the Earth's surface. So we have really old Precambrian rocks before 545 million years formed, and these are exposed at the Earth's surface. The platform, on the other hand, would be the ancient part of the craton that's covered with Phanerozoic or newer sediments, sediments that were emplaced after 545 million years ago. So shield is exposed, platform is covered with newer sediments. And here we see the shields of the continents. Note the Canadian shield of North America. Check out the mountain belts as well. And there are younger rocks that are covering parts of the shield. And this would be platform. Up close and personal with the Canadian shield, it's that light color. The Precambrian rocks that are covered are shown in sort of a peachy color. This would be the platform. Together, the shield and the platform form the craton of North America. Okay, that's going to conclude this discussion on deformation, mountain building, and just a very brief overlook at the continents. when you take Earth history, you will get into continental evolution and changes in North America, particularly in much more detail. This is only an overview, so if you have any questions, please feel free to post them on the discussion board or email your instructor. Thank you so much for joining me, and have a great day.